We have a function f of xy equals y squared over x, and we're asked if there's a 3% uncertainty in the value of y and a 4% uncertainty in the value of x. Looks like I didn't complete my word there. What is the maximum reasonable uncertainty you would expect in the value of y squared over x based on these two uncertainties, the uncertainties in y and in x? Now, it helps to understand what's going on here. It helps to sketch this, hopefully by now familiar picture. Okay? And first of all, well, let's interpret 3% uncertainty in y, 4% uncertainty in x. Okay, a 3% uncertainty in y means that if delta y is the uncertainty in y, that delta y over y has to equal plus or minus 0.03. Okay, in that case, for reasons that you should understand very well by understanding what percents mean, if delta y over y is plus or minus 0.03, that means delta y, your uncertainty in y, is plus or minus 3% of the value of y. And similarly, delta x over x would be plus or minus 0.04, which means that delta y would be, now I wrote it as 0.03y and delta x as 0.04x. Actually, we would say, that's a plus or minus and that's a plus or minus. Using just the plus to draw the picture, remembering that delta y could go in that direction, delta x in that direction, we let delta y equal 0.03y, delta x equal 0.04x, and draw the picture of the changes that occur in a linear approximation to y due to these two changes, to y and to x. Okay, so the change that you have in the value of y squared over x due to this change in y is just going to be fy times delta y. And that's going to be approximately what? Well, the y derivative is 2y over x multiplied by 0.03y. Okay, and over here, fx delta x, fx being easily calculated, it's going to be negative y squared over x squared. Multiply that by your 0.04x, and you get the change in the value of the function, the z coordinate, due to this change in x. Okay, well, yeah, I'll say one more thing. And of course, if delta y goes in this direction, then your fy delta y would be negative. If delta x goes in that direction, then fx delta x would be positive. And you should be able to see that easily based on the picture. Okay, well, our change in f, now I'm going to write down the differential. The differential df is just fx dx plus fy dy. So that your delta f, your change in f, should approximately be equal to fx times delta x plus fy times delta y, which is just what we get from this picture. Okay, so this is a differential. This is actually our approximation to change in f based on the differential, and there's a clear connection that I'm not going to elaborate right now. Okay, this means then that delta f should be negative y squared over x squared times 0.04x plus 2y over x times 0.03y, just the quantities that we get here. Okay, now I'm just writing down the positive quantities because I want to show how something works out here. And I'm not sure how I got an equal sign down here, but we'll talk about it in a minute. Okay, yeah, I see what I did. Okay, now we got delta f over f, which is the uncertainty, proportional uncertainty in f that could be expressed as a percent. So we would take delta f over f and express it as a percent. Well, we just take our delta f and divide by f, which is y squared over x. So we divide everything here by y squared over x. Now I didn't rewrite all this, I just put some dots over here because you can easily divide each term of this by y squared over x. When you do, you're going to get, of course, the reciprocal of this, x over y squared multiplied through if you multiply that out, all your x's and y's go away, and you just get proportions. If you do this according to these numbers, you can verify it. You get negative 0.04 plus 0.06, which is negative 0.01. Some rocket scientist wrote this down wrong. That's obviously, it's not even negative, it's positive 0.02. I don't know where I got negative 0.01, but I have to admit that I'm the guilty party that wrote that. Okay? Now, the point I was making here is that this is less than either of these, the magnitudes of either of these uncertainties. You want the maximum possible magnitude, and remember that just by letting delta x go in the opposite direction, we can make this positive. Letting delta y go in the negative direction, we could make this negative. We can make this change negative. But what I choose to do to maximize the uncertainty is I'll choose the direction of my delta x so that my x uncertainty becomes positive. And that means I'm going to choose, instead of 0.04x for my delta x, I'm going to use the negative 0.04x. Using the negative 0.04x, I'm going to get a positive 0.04 here to match up with the positive 0.06 I got here and give me the actual maximum uncertainty, percent uncertainty. That would be 0.10, which of course is the same thing as 10%. Okay. Now if we trace where we got 10%, according to the rule that you might have gotten in the early part of your course, that was stated in the first chapter, y squared, you're going to double the uncertainty in y. X's first power, you're just going to use the uncertainty in x. And this is a division or a multiplication, in this case a division, so you're just going to add the uncertainties. This is why you do that. So we add doubled the 3% y uncertainty to the 4% x uncertainty, and we get a 10% uncertainty. But in terms of the differential that everybody in this course right now has experienced in multivariable calculus, you get the same thing using the differential. And the reason for those rules that you were given in Chapter 1 is the differential. Okay, so this shows how it works out.